for the acceleration. I take the same example as before. Okay, you remember this is like taking a high-speed camera. You take pictures at different times, and then you can look at each frame individually. Okay? So, if you look at the acceleration of the center point of the ball at different instants, what type of motion is point A having over here? What is it? Point A is moving in what? What type of motion is it having? Translation only, no? But basically the real motion of point A is translation. Okay? Now, what happens if at each one of these instants we decide to study the motion from the point of contact of the ball with the ground, so the point at which it is rotating? Yeah? So in that case, it will look like at each one of these instants, it will look like the ball is rotating about the point of impact about the point of contact of the sphere with the surface. Yeah, so this one will be different instantaneous centers. We agree? The motion of point A is just translation and only has a component in what? In the x direction. Yes? Okay, so we're good. So we agree with that. That's not a problem. So now let's see what would happen mathematically. So what happens if we calculate the acceleration of point A from the instantaneous center? So what will be the equation? Acceleration of A from the instantaneous center will be equal to what? Acceleration of at the instantaneous center plus alpha cross r of A with respect to the instantaneous center minus omega squared r of A with respect to the instantaneous center. Okay? So here I'm going to leave this acceleration of the instantaneous center as a variable, and I'm going to do the other ones. So here we know the acceleration of A only has one component on the x. Okay, we know that. So now what should be the tangential? Should be equal to what? 0, 0, alpha. What is the position of A with respect to the instantaneous center? Okay, so it's 0, r, 0. What would be the normal or centripetal acceleration? Minus omega squared of what? 0r. So now what happens over here? We have the acceleration of instantaneous center plus what? What would be this one equal to? Minus alpha r plus 0 minus omega squared r. Okay, so let me rewrite very quick the same equation on the next page. So basically we have the actuation of A equal to the actuation of the instantaneous center plus, I'm running out of colors, minus alpha r0 plus 0 minus omega squared r. Okay, so basically what is the left-hand side saying over here is that the actuation of A only has a component on the x. But this equation is showing a component on the x and on the y, no? Yeah? So then I of c should do what? Should try to cancel this one. Does that make sense? Yeah, so that we only have a component on the x. All right, so that left-hand side only has actuation of ax component. What should we have? The actuation of the instantaneous center should be equal to what? Zero plus omega squared r. So an instantaneous center has zero velocity. Velocity 0. But the actuation is not 0. Okay? So if I do a figure, we know the actuation of point A is only translation, and this point over here, from which is rotating, this point here is an instantaneous center. What does instantaneous center means? Velocity of the instantaneous center is 0, which is true because this point is not moving, no? Yeah? But what happened when you study this motion of the motion of one object? What happened when you study the motion of point A from this one? The motion of point A from IC is only due to rotation. So that means that it will look like it's rotating about this point, no? Yes? But we know, regretfully, that the rotational component of the velocity always yields to two components. So really, in this point here, what are you going to have? You're going to have this component here, from here will be equal to what? To the normal or to the tangential acceleration? What is this one? Normal or tangential? What is it? Normal? Really? This is tangential to this circle, no? Yes? So really, the normal acceleration is equal to alpha cross what? R of A with respect to the IC, which is what we did over here. If you look at it, this equation, this term is equal to what? Alpha R, no? But now, what do we know? We know that, regretfully, when we do this, it gives us two components. So here we should have the component minus omega r, one going down. But we know that one does not exist. So the acceleration at this point here needs to do what? Needs to cancel this component, no? Which is the one we put over here. So if you plot it, what would be that component? It would be the one over here from the Instantaneous Center going up in order to cancel this one. Did you follow basically what I just showed you? I'm not asking you if you fully understand it because there's a reason why I'm recording this. Because that way I don't have to explain it 15 times. Yes?
I'm having trouble understanding the rotation of the IC.
Okay, so this is rotating. So this, at that instant, is doing this. Is this? It's rotating. The problem is that, remember that the velocity, the rotational velocity yields to two components of acceleration, no? But because the motion of point A is really what? Just translation, the motion of point A is not rotation, it's really translation, no? So it's only being affected by the tangential component of the acceleration and not the normal. That's basically what this means. All right, so let me stop the video here.